Good afternoon, everyone. Thank you very much for inviting me to be the keynote speaker at the 8th Brazilian Congress on Knowledge Organization. In this talk, I will tell the story of a life spent working on knowledge organization systems, COS, from faceted vocabularies to generative artificial intelligence. Language generation has a long lineage. I will briefly discuss the Getty Vocabulary Program, the origins of ENCOS, Network Knowledge Organization Systems, Metacode content processing pipelines and knowledge maps, AI before language generation, what made large language models, LLMs, possible, and RAGs, Retrieval Augmented Generation. Like organic web search, I think LLMs are an example of an information technology that has the potential to deeply enhance human expertise. But too often, information technology is seen as a means to replace the inefficiencies of people. I will talk about the challenge of how to effectively program generative AI using natural language instead of the old programming languages. I think that COS will play an important role in this, but we will need to define concepts and relationships in ways that can more readily be consumed by LLMs. Over the last few years, I've organized ENCOS workshops on COS and AI in COS. I will share with you what I've learned about the future of COS and AI from these workshops. In 1997, I organized the first ENCOS workshop as part of the second ACM conference on digital libraries held in Philadelphia. ENCOS stands for Networked Knowledge Organization Systems. At the time, I was working for the Getty Art History Information Program, which was the Getty Foundation program that supported the development of the Art and Architecture Thesaurus, known as the AAT, as well as the Thesaurus of Geographic Names, known as TGN, and the Union List of Artist Names, known as ULAN. These are the so-called Getty Vocabularies. We also supported the development of art and architectural history indexing services, as well as digital archives projects related to the provenance of cultural objects and the rediscovery of antiquities during the European Renaissance. Besides designing the means to publish and maintain the well-known Art and Architecture Thesaurus, described in a chapter in an American Society for Information Science monograph titled Studies in Multimedia, a major contribution to the field of knowledge organization was the so-called Getty Systems Data Model, described in a paper published in the proceedings of the Second International ISCO Conference, which was also a primary inspiration of the CDOC Conceptual Reference Model, CRM, an ontology for concepts and information in cultural heritage and museum documentation. To give you a flavor of the state-of-the-art in multimedia information systems in the early 1990s, this is a picture of Arnold Nesselrath, the director of the Census of Antique Art and Architecture known to the Renaissance Database Project, giving a lecture using the system, which included 2 video discs and 2 monitors integrated with a relational database running on a Unix computer. That's me, following a script where I typed in queries to retrieve data and images to illustrate Arnold's talk. Arnold is currently Professor of Art History at the Humboldt University in Berlin. From 2009 until 2017, he was Director of Art History Departments of the Vatican Museums. From the same period, this is the official group portrait from the OCLC NCSA, that's National Center for Supercomputing Applications, Metadata Workshop in 1995, which was the first Dublin Core workshop. I didn't attend the workshop, but the Getty sent a representative from my team. The Dublin Core became the de facto standard for metadata description of web pages. And it's been adopted by Microsoft and Adobe, and it's evident in many widely used software products to this day. The National Center for Supercomputing Applications is perhaps best known for developing the Mosaic browser, which was instrumental in popularizing the World Wide Web by integrating multimedia such as text and graphics. Mosaic was the first browser to display images in line with text instead of a separate window or a separate screen or on separate screens like the Census multimedia system. This was the early days of the World Wide Web, and it was just beginning to open up beyond the research scientific organizations like CERN, l'Organisation Européenne pour la Recherche Nucléaire, where the web was first invented by Tim Berners-Lee, to libraries, archives, and museums. For the first ENCOS workshop at the second ACM Digital Libraries Conference, I invited my colleagues who were doing interesting work on developing faceted indexing schemes for the Getty, such as at the Bibliography of the History of Art, the Modern Language Association International Bibliography, and other resources. In retrospect, I think we had an awareness that we were on the verge of a major digital transformation in libraries, archives, and museums, but we certainly didn't realize how dramatic and complete this change would be over the following years. Nor did we imagine that the ENCOS workshop would continue to this day. At the time, computers were still very limited in terms of processing speed, memory, and storage. Like dinosaurs, they were physically large, but with very small brains. The main thing about the web was that it began to be possible to connect computing devices together so that local storage and processing power became less problematic. The infrastructure began to be built where you could easily look things up online at little or no cost. 1 year later, in 1998, after 10 years of working in the culture sector, I was recruited at the American Society for Information Science meeting in Portland, Oregon, to work at a .com startup company. This was not a .com that wanted to sell stuff online. It was a company that wanted to organize very large amounts of content to try to resolve very complex problems. My job title was Vice President for Information Product Development. The Data Fusion Company was the brainchild of Joel Schatz, who had made a lot of money building a mobile telephone network in Russia after the fall of the USSR. He was a proponent of systems dynamics, a methodology and mathematical modeling technique to frame, understand, and discuss complex issues and problems. Joel wanted to build a tool that could visualize inputs, processes, and outputs with knowledge maps. Knowledge mapping is a structured process that visually represents the flow, storage, and access to knowledge within an organization. Joel wanted to develop a tool that could visualize big systems and the relationships between entities, systems related to water resources, air quality, transportation, and even world peace. These sorts of systems models needed content, lots of content, and lots of that content was not structured much or at all. To make that less structured content useful, we needed to develop a content processing pipeline that could apply language processing methods iteratively to break down the narrative into meaningful chunks and then identify and disambiguate the named entities. Finally, the content needed to be analyzed to determine what it was about and why it was important. Once we had built a highly curated collection and tagged the hell out of it, we could generate visualizations of the relationships among the named entities within the chunks and ultimately construct many narratives. Sounds a little like generative AI. It was, except without any of the computing power that we have today. Simply put, n-gram level tokens were out of the question because it was simply impossible to hold a large enough matrix in memory to compute relationships at a very granular level. Indexing is one of the core functionalities of information retrieval. In addition to natural language processing and entity recognition, we needed to do content tagging at scale. In 1998, a number of information retrieval engines using vector and probabilistic statistical methods were available as open source or as licensable OEM products. Latent semantic indexing and clustering were still primarily in research and development. We opted to implement a vector method because it generally performed better in our testing. The challenge was to build training sets. While we focused on domains where there was readily accessible, well-categorized content, such as medicine and law, we were constantly asked to build general-purpose categorizers for common business functions, but we failed to be able to do this effectively. At the same time, the web search engines were beginning to be available on the fledgling World Wide Web, quickly displacing the Yahoo and DMOZ topic trees for browsing. AltaVista was the first web search engine to become wildly popular until it was overtaken by Google in 2000. Previously, online searching was only available through expensive timeshare services or on-site at some research libraries. It was limited to a few published subject indexes, required training and expertise to use effectively, and only got you a bibliography, not usually the full text of items. Web search engines were accessing full-text resources limited only by what was available on the web. Access was free, and the user interface was extremely simple: type and go. But under the hood, the democratization of online searching was ranking search results by popularity rather than Boolean searching subject and named entity indexes to find relevant and comprehensive results. While everyone could use Google, not everyone was able to get good search results. Even with the dead simple user interface, choosing effective search terms and knowledge about Google's syntax could enable better search results. For many, the new millennium seemed like the golden age for information access. In 2000, data fusion was renamed Metacode. Metacode was the name given to the unique identifiers assigned to concepts and knowledge maps. This was an early implementation of namespaces and universal resource identifiers, URIs, and one of the first instances of assigning URIs to concepts, such as terms in a controlled vocabulary. While Metacode predates SCOS, the SCOS data model views a knowledge organization system as a concept scheme comprised of a set of concepts. We built a vocabulary management tool for creating and managing metacodes, a content tagging pipeline for assigning metacodes to content items, implemented a metadata database for storing metacodes associated with content objects, and provided a graphical user interface for viewing and browsing metacodes in knowledge maps. By the end of 2000, we had a few early customers, and Metacode was acquired by Interwoven, a publicly traded web content management company, for the astounding price of $150 million. Interwoven rebranded the product as Metatagger, emphasizing the content tagging pipeline for automating the generation of metadata to enable methods of publishing dynamic website content. After spending 2 years building information product domains at Metacode, I spent the following 2 years working at Interwoven, promoting tagging content with metadata. Think of this as moving from building the art and architecture thesaurus ontology for material culture to promoting the use of Dublin Core metadata for cataloging content. Interwoven was a much larger company than Metacode. I was assigned to work in field sales, which means that I went on calls with sales professionals all over the world to all kinds of businesses and organizations in many different sectors who were all trying to figure out how to do business on the World Wide Web. My job was to promote metadata tagging using the Metatagger product as a part of the Interwoven web content management ecosystem. I had the job title of Content Commando. I was exposed to myriad use cases every day of the week. It was overwhelming, and a crash course in business information management. The business organizational concerns about how to make money and stay out of jail may not have been as lofty as data fusion's concerns about water, transportation, and peace, but they were more immediately actionable and measurable. One of those sales calls was to NASA's Jet Propulsion Laboratory, JPL, which became the first project of a new company, Taxonomy Strategies, that I would form with my former Data Fusion chief scientist, Ron Daniel. Taxonomy Strategies worked with JPL to develop the NASA taxonomy from 2002 to 2005. In 2003, Taxonomy Strategies created the content model for the first U.S. government web portal called firstgov.gov and now usa.gov, and later developed Web 1.0 information architectures for many U.S. government agencies. Taxonomy Strategies also developed the first online shopping taxonomy for Home Depot, a large home improvement retailer, in 2003, and then went on to develop consumer and business-to-business online shopping taxonomies for many well-known companies like Dell, Nike, and Oracle. By applying the lessons learned at Data Fusion, Metacode and Interwoven, Taxonomy Strategies had the opportunity to work on dozens of projects in various sectors that have helped to make digital assets easy to find, use, and share. In retrospect, the Data Fusion startup company neglected to pay enough attention to certain aspects of artificial intelligence that emerged in the late 1990s. While we made the right decision to focus on natural language processing, we should have taken machine learning neural network research more seriously. But we had a reluctance to embrace black box technology. We were more interested in automatic classification, especially using predefined knowledge organization systems such as NAICS, MESH, and the AAT. We conducted experiments to optimize the process of building training sets. Generally, this required finding costs with well-categorized content. But the biggest challenge was finding discrete training sets, meaning content that was about one discrete concept, and a critical mass of these examples. We didn't attempt to build any machine learning with regression and recurrent processes and processing, and to be honest, we didn't have the expertise to do that in our team. Data Fusion was 5 or 10 years too early to be able to commercialize machine learning. The real resurgence of neural network research didn't happen until 2005, and the graphical processing unit, or GPU, only began to be used to rapidly perform the really large numbers of calculations required by machine learning neural networks in 2010. But Data Fusion demonstrated the value of COS and rich metadata in web content management, even if the automation of its production was rudimentary. While the GPU has provided the computing horsepower for the current generation of AI, the key innovation that characterizes the current generation of AI is a special type of neural network architecture called a transformer. Transformers enable neural networks to keep track of patterns in their input using self-supervised learning on large amounts of raw text, generally taken from the internet. This is highly effective for natural language processing and natural language generation, as illustrated by large language models like ChatGPT, Claude, Llama, and DeepSeek. These models are trained to analyze text and estimate the most probable word following a given sequence. Because these models are trained on enormous amounts of content, 13 trillion tokens, or the equivalent of 80 million books, more than twice the number of books in the largest research library imaginable, they are very good at the task of language generation. Another remarkable aspect of the current generation of AI is that the user interface is natural language. When you provide instructions to an LLM, it is very reminiscent of a web search engine. In the LLM ecosystem, natural language queries are called prompts, and the generation of prompts is called prompt engineering. You can think of web search engines as examples of so-called zero-shot prompts, meaning that you type in a query and get a response, even though the prompt itself was not necessarily part of the training data for the model. Also, with a zero-shot prompt, there is not necessarily an intention of iterative prompting. The choice of terminology, style, and format of the prompt is very important. Changing a single word can significantly alter the output. Prompts need to be precise, avoid jargon, use punctuation, and be structured like a use case. Meaning, it should identify your perspective or role, who you are, what you want to know and why, and how you desire the output to be formatted. This table illustrates a zero-shot prompt template and some example prompts. More interesting than zero-shot prompting is effectively dialoguing with an LLM. This can be with a few examples, or can be through reasoning or thought generation, decomposing a complex problem, providing verification, or a combination of perspectives, and there are other techniques. Chat user interfaces to LLMs keep a record of each session and provide an option to start a new chat. This provides an opportunity, at least for immediate or near-term iteration, without any programming. An interesting development is the emergence of prompt collections and libraries. These are curated prompts grouped by broad categories which are free and for sale. The good news about AI is that everyone is fiddling with it. The bad news is that the results are unreliable. I think it's similar to the experience with web search. Everyone is looking things up. The results are good enough. This search provides answers to simple questions, but it can be frustrating to get definitive answers, find a known result, or do any sort of in-depth authoritative research. To improve the reliability of search, you need to use better search terms. One way to do this is to look for and choose search terms with COS. The same is true for improving the reliability of COS. I remember interviewing an art historian many years ago when I was working at the Getty Trust. I asked her, "How do you use the art and architecture thesaurus?" She answered, "It helps me think." The approaches to integrating COS into prompts are the same as for integrating COS in information retrieval. They are incorporate synonyms and quasi-synonyms in the prompt using a domain thesaurus, broaden or narrow the concepts in the prompt using a hierarchical taxonomy, or provide specific contexts using facets such as content type, geography, language, time, process, or other contexts. While it's possible to manually refer to COS while writing prompts, LLMs integrate with other systems through the context window. The context window is the input text that the LLM can process. LLMs predict the next token based on the input sequence, and by manipulating this input, one can affect the model's output. The ChatGPT context window is capped at 32,000 tokens. A token is roughly equivalent to 4 characters, or about 3/4 of a word. But processing large context windows can be computationally expensive and slow. An application programming interface, or API, allows for development of applications that can integrate additional resources, such as COS and search results, into prompts. The ChatGPT context window in this case, is up to 1 million tokens when accessed via the API. In this context, COS can also be used to guide language generation results by identifying entities in the output, linking entities to knowledge graphs, and connecting models to knowledge bases. Indexing source content to improve document recall and precision, and annotating the output to improve explainability and trustworthiness. Retrieval Augmented Generation involves searching for relevant facts and inserting them into the context window to improve the model's answers. The approach can be expanded to include various data sources beyond search engines, such as an indexed domain-specific collection, databases, and calendars, making it a complex but powerful tool for enhancing LLM performance. The response may include annotations, such as source citations or bibliographic references from the domain-specific collection content. A good way to think about RAG is as a method for pre-processing LLM prompts to make them more responsive to domain-specific questions. A knowledge graph is a representation of the relationships among named entities. A knowledge graph may be queried in the RAG method to improve the information retrieval with equivalent terms, but especially to provide associative typed related concepts. It can also be integrated as a post-process to an LLM response to identify possible refinements through reasoning, decomposition, verification, or other methods. RAG applications may use information retrieval in different ways. In particular, they may not necessarily index content using COS. They may use vector search to identify similar content statistically without any reference to COS. A better way to achieve more reliable and measurable and better recall and precision is to use vectors to map content to COS and then to use COS to identify similar content. The good thing about standards is that there are so many to choose from. The same is true of COS. Bartok, the basic register of thesauri, ontologies, and classifications, is a database of COS and lists over 3,700 resources. ISO has more than 900 terminology standards. Some of these are standards about how to create and manage terminologies, like ISO 25964 Part 1, Thesauri for Information Retrieval, Management, and Use. Others are standard domain-specific terminologies. It is challenging to manage terminology and vocabularies in various fields, and particularly in biomedical science. Existing systems, like the Unified Medical Language System, or UMLS, has more than 105 sources, and these are often inconsistent and they are complicated. This is a big challenge for the AI community. This is a big challenge for developers. They are simply not equipped to deal with the intricacies of assessing and selecting COS and integrating them appropriately into general purpose applications. LLMs make it easy to get to 80% accuracy quickly, which can lead to ad hoc solutions rather than systematic approaches. This is one of the reasons that AI has generally avoided COS. It has been left to consultants to develop custom applications for niche industries where the benefits of more precise retrieval outweigh the difficulties and costs of COS integration and development, or to researchers. However, I think there has always been an interest in a general purpose categorizer for common business functions, just as there is an interest in universal classification systems for organizing content collections, such as the Dewey Decimal Classification, the Library of Congress Classification, the Universal Decimal Classification, and Integrative Library Classification, and there are others. I would argue that general purpose systems would be welcome as part of the AI ecosystem, assuming that they were intuitive, easy to use, kept up to date, and free. The Network Knowledge Organization Systems/Services Workshop, or ENCOS workshop, has been convened annually since 1997 in the US and/or Europe, and occasionally in Asia. ENCOS is devoted to the discussion of functional and data models for enabling knowledge organization systems, services, or costs, such as classification systems, thesauri, and ontologies, as networked interactive services to support the description and retrieval of diverse information resources. According to Traggett-Cock and my co-chair Doug Tutto, knowledge organization systems services costs model the underlying semantic structure of a domain. Embodied as web-based services, they can facilitate resource discovery and retrieval. They function as semantic roadmaps and make possible a common orientation by indexers and future users, whether human or machine. Although incorporating cost and information retrieval applications has been a long-standing interest of ENCOS, the current co-organizers, Marcia Zeng from Kent State University, Douglas Tudhope from the University of South Wales, and myself began focusing on costs and AI in 2023. The workshop, held in Daegu, South Korea, in conjunction with the International Conference on Dublin Core Metadata Applications, included 2 presentations. This was followed by 2 workshops in 2024 and one in March at the biennial ISCO conference in Wuhan with 4 presentations, and one in October at the International Dublin Core Conference in Toronto with 10 presentations. Finally, a special issue of KO, Knowledge Organization, is in preparation with 5 research papers. These materials cover various approaches to using LLMs as tools. The presentations from the workshop series and the resulting publication fall broadly into 4 categories. They're projects that are building more consistent ontologies and taxonomies, or cost management. There are projects that enhance resource description with more complete and consistent metadata and annotations. There are projects of applications of cost-based classification. And finally, there are projects that are conducting domain studies of large language models and cost users and uses. The range and breadth of this work is impressive. As a co-organizer of the ENCOS workshop and co-editor of the special issue on costs and AI, I've had the opportunity to read and review most of the submissions and to listen to and moderate the workshops. I've reflected on these many and varied research projects and marveled at the inspiration and creativity and level of interest and engagement with AI. But I also think that the key consideration is how language generation can be mastered as a tool to enhance human expertise. And this is, after all, the whole point of technology. I am as convinced as ever that costs and collection development or content curation will be a critical component of the emerging AI ecosystem. There is much work that needs to be done, and librarians and information scientists are well equipped to do it. This is as exciting a time as I can remember to be engaged in working with information and people. Thank you.